Okay, so this video is about comparing sequences to functions. So we've talked about different types of sequences, talked about arithmetic and geometric, okay? So we have a couple things, all right? So the first thing that I want you guys to copy down is that sequences are functions since each input has only one output, right? So if we remember our arithmetic and geometric sequences, right? I have, numbers, term numbers, and then the output. So we always start with 1, 2, 3, 4. And no matter what, right, if it's t of n is equal to, 3n plus 1, I know that when I plug a 1 into this equation, right, if I say t of 1, 3 times 1 plus 1, I know I'm always going to get out the number 4, right? If I plug a 2 in, right, I'm always going to get out 7 and so forth, okay? So they're always functions. That means that they'll pass the vertical line test, okay? The second thing we can copy down is this. Sequence domains are limited to positive integer values, right? While functions can be any number, okay? So the second that I see t of n, I can only plug in the numbers, right? 1, 2, 3, 4, 5, etc., right? If I see f of x is equal to 3x plus 1, I can plug in all real numbers. I can plug in all real numbers. Okay, you're still going to get 4 and 7 when you plug it in. This one would be connected, right? While this one would be discrete. And that's the third thing that we're going to copy down, right? Sequence graphs are discrete, meaning they're not connected, while functions are continuous, meaning that they are connected. So we're going to walk through a problem that kind of talks about the differences between sequence and functions. So here's our problem. Okay, so let's consider the sequence -5, -1, 3, and 7. So we want to create some multiple representations, okay? So if you can, pause the video and try to make a table and connect those that table to a graph, and then let's come up with an equation, right? And again, it could be recursive or explicit. You can try both. I'll put both up there. So go ahead, pause the video now. Okay, so if we're coming back from our pause video, what we should have noticed is, again, we're going to have n, and we'll say t of n, and our numbers are, the first number will be -5, the second number is -1, the third number is 3, the fourth number is 7. So if I was to connect these points together, or sorry, if I was to plot these points, right, I know that this will be 1, and then I'm going to go down 3, 4, 5, so -5. There I'll be at 2, and then -1, be at 3, and then 1, 2, 3, so I'll be at 3. And so what it should start to look like is it should start to look linear, okay? Instead of looking at that graph, we can look right here. I've graphed it for, have a better graph, okay? So it looks linear because this is an arithmetic sequence, okay? So again, it follows the linear path. And so if we're going to come up with a recursive equation, right? So we're going to have t of n, explicit equation, either one. So we'll say t of n is equal to our common difference times n plus our y-intercept, or our initial point. So for explicit, we would say t of n is equal to, what do we notice? We go from -5 to -1, -1 to 3, 3 to 7. Our common difference is 4, so that's our slope. And then the term that came before -5 should have been -9. Okay, so that would be our explicit one. If I'm going to do a recursive, remember there's two parts that I need. I need a starting point, so I'll just put my first point as my starting point. So t of 1 is equal to -5, and then I will say t of n plus 1, and I'm going to say t of n plus 4, right? So the red goes with the red and the blue is the explicit, right? So recursive is the red. So then it says, is 400 a term of our sequence? Now, you could continue this sequence and be like, all right, my 5th term is 11, my 6th term is 15. I could continue that, but that seems like a lot of work, right? So what else can I do is I want to know, is this going to be an output? So all I'm going to do is I'm going to set 400 equal to 4n minus 1. I'm going to set it equal to my explicit equation, and then we're going to solve. So I'll add 9 to both sides. So I'll get 409 is equal to 4n. I'm going to divide both sides by 4, and 4 does not go evenly into 409. So we're going to get, so 4 goes into 4 one time, which is great. And so we'll get 0 here. We'll bring down our 0. 4 does not go into 0, so we get to put a 0 here. And then 4 goes into 9 2 times, right, with a remainder, excuse me, of that dog. And then what we're going to do is we'll put that in decimal place, bring down 0. 4 goes into 10, right, 2 times. 2, get another decimal, so 4 goes into 20. 5 times. So we get 102.25. That is not a positive integer, right? So that's not a positive integer, which means that 400 is not a part of our sequence. So we get to say no, and the reason being because it's 102.25. Okay. So now what's the main difference on the second one, right? So we want to create the same multiple representations as we did in part A for this new function, f of x is equal to 4x minus 9. So again, we want to think about how are f of x and t of n different, and how can you see their differences in each of these representations. So go ahead, again, pause the video and see what you make of it. Okay, so what's going to happen is, so how are f of x and t of n different? Okay, well, first off, what I'm going to do is I'm going, let's see if I can, no, I'm going to take away my, I'm going to take away this, and we can see that our table, so I'm going to take away part of our long division, which should already be on your paper. So we can see from our table that, yes, we see the same first 4 numbers, -5, -1, 3, and 7, but now notice that I can plug in other numbers, right? I can plug in 0, I can plug in -1, -2, -3, and we are going to connect the points together. And again, what this means is that every single point that is on this line is a solution. Okay, so again, what's the main difference is that f of x is a function, okay, and t of n is a function, right? But, right, f of x is continuous, while t of n is discrete. Okay, so for the function f of x is equal to 4x minus 9, is it possible to have an output of 400? Yes, because that means that our x is actually 102.25, and I'm not going to go through the whole long division once again. And again, I'm just going to bring us back up to here, right? I can plug in any value into just a normal function. If I'm only doing a sequence, I'm only doing my positive integers. Okay, so here's our main difference between, we have 2 problems. One's a sequence and one's a function, okay? All right, so there's a couple things that I want to make sure that we understand and we can copy down. So equations for sequences, let's just make sure that we have all this down. Arithmetic sequences for explicit only, right? We are going to use the t of n is equal to m times n plus b, right? M is the common difference. We can also say this, t of n is equal to dm plus b, okay? Now, something that is different, right, is we also have what's known as alternative notation, okay? And so this is just another way that we can talk about sequences. So instead of t of n, is an A subscript n, right? And instead of our B value, A of 0, we're going to use A of 0. So that's telling us that it's your first term. So if we see A of 0, that is our 0th term. If we see A of 1, that is our first term. If we see A of 4, this is our 4th term. So basically the 4 is just a subscript, okay? So make sure that you have this copied down into your notes. And if you don't have your sequences up above, please make sure you copy that down as well. Okay. Now, this is all for arithmetic sequences. What about our geometric sequences? Right, geometric sequences, again, we say T of n is equal to our A times our B to the power of n. Okay, and so again, our B is our multiplier or our common ratio, right? N is the term number, A is our 0th term. So again, alternative notation right here is we can say A sub 0 times B to the power of n. Okay. And again, if you want to read about recursive sequences, right, is a sequence in which each term depends on the term before it. But really, I'm just pointing this out because I wanted to make sure that we have alternative notations in our notes. All right. Last but not least, let's go ahead and what I want you to do is I want you to pause the video and I want you to try these 4 problems on your own. So the first 2 problems, you're just writing the first couple of numbers in your sequence, and then you're going to come up with an equation for your sequence and to see how you do. Okay, so go ahead, pause your video right now, and then when you're done, come back and press play so that way you can see what you did. Okay, so if you've pressed play, you've paused the video and tried it out. So if we have our first term, so this would be A of 1 is equal to 3/2 times 1 minus 1. So this will be 3/2. I'm going to change the 1 to 2 over 2. So this will just be 1/2. So my first term is 1/2. A of 2 would be 3/2 times 2 minus 1. So this is really 6 over 2 minus 1, which is 3 minus 1. So that gives us 2. A of 3 is 3/2 times 3 minus 1. So 9/2, that won't be able to simplify, so I'll put 2 over 2. 9 minus 2 is 7/2. And again, you can keep these as fractions or decimals. I'm going to leave them as fractions. So this will be times 4. So 12 over 2 minus 1 is 6 minus 1. So this should be 5. And then last but not least, A of 4 would be 3/2, oh sorry, A of 5. My bad. A of 5 is 3/2 times 5 minus 1. So 15 over 2 minus 2 over 2. So 13 over 2. Excellent. Okay. If we're going to do part B, so let's do part B in red. So A of 1 would be 1/4 -8 to the power of 1. So that will be 1/4 times -8. So -8 over 4 is -2. Perfect. A of 2, so 1/4 and -2. So this will be 1/4 times 64. So it turns positive, and then 4 goes into 64 4 times. 16 times. That number should be 16. Sorry. So I'm going to put 16 right there. And then A of 3. So this will be a -8 to the 3rd power. So basically we're going to multiply 64 by -8. So I'll have 1/4 times a -512. So then I'm going to get -128 as my answer. Okay. That was our first one. Write an equation for this sequence. So -4 to 4 to -4 to 4. So I noticed that it's not adding by the same number consistently, because this would be a +8 and then this would be a -8. So I don't want to say it's arithmetic. But I do notice that if I multiply by a negative number, if I multiply by -1 each time, -4 times -1 gives me +4. 4 times -1 gives me -4. -4 times -1 gives me +4. Pretty confident that's my multiplier. So I'm going to say my multiplier is -1. And the term that came before it, so a of 0, would be a +4. So that means my equation would be 4 times -1 to the power of 1. Or sorry, power of n, not power of 1. Okay, and again, we can test this out. If I plug in a 1, -1 to the power of 1 is just -1. -1 times 4 gives me -4. And then so forth and so on. Okay, so last but not least is part D. So I notice that the numbers are not increasing too quickly, so I'm pretty confident that this one is arithmetic. So 7 plus 6 gives me 13, and 13 plus 6 is 19, and 19 plus 6 is 25. So I know that my difference is 6, and the term that came before a sub 0 should be the number 1. So again, a of n is equal to the difference, 6 times n, and then plus 1. Okay. So that's that one. So for this one, I'm going to have it on a separate slide so we can do a little bit more work. Okay. So here it is. So Janine was working on her homework, but lost part of it. Oh, Janine. She knows that one output of P of R is 2 times 5 to the power of R is 78,000, but she cannot remember if P of R is a sequence, a function, or could it be both, right? So we want to kind of help her figure this out. Okay, so we want to figure out, is it a sequence or a function? So basically what I can do is I'm going to try to eliminate if it's going to be a sequence. So if I start like plugging in some numbers, so P of 1, so this would be 2 times 5 to the power of 1, so 2 times 5, which just gives me 10, okay? So P of 2 is 2 times 5 squared, so this would be 2 times 25, which gives me 50. So if it's a sequence, right? So if it's supposed to be a sequence, I know that I'm going to plug in an actual integer and I'm going to get out 78,000. So if a sequence, it will be in this column. So 5, 6, maybe 7, right? If it's a function, so function, if the input is not a positive integer, okay? And so this is where we kind of need a calculator. So let me start plugging in some numbers. So power of 3, so 2 times 5 to the power of 3. So 5 to the power of 3 is 125. And I'm going to multiply that by 2, so I get 250. Right? So I'm pretty confident we probably have to go somewhere down here. So I'm going to try 6. So let's just skip ahead and say 2 times 5 to the power of 6. Now, I don't have a calculator, so I'm going to use Desmos. So let's pop this up to Desmos really fast. So 2 times 5, 2 times 5, times, 5 to the power of 6. All right, so pretty close. So now what about 2 times 5 to the power of 7? Okay, so if we notice that 2 to the power of 6 gives me 31,250, and then 2 times 5 to the power of 7 gives me 156 and 250. So 3125, and so let's put that information down on our previous slide. So let's come back over here, move it over here. So what did I say? That was, so this was 31 250, and I believe this was 156, 250. Okay, so notice that the 78,000 would be somewhere in between here. Okay, so 78,000 is somewhere between 6 and 7. So this is not going to be a sequence. It's purely just a function. Okay, and so notice that if I kind of come back to my calculator, if I come back to Desmos, what happens if I start plugging in decimals? So if I say 5 to the power of 6.5, right? Notice that I get close to 78,000. So it's higher than 6.5. So 2 times 5 to the power of maybe like 6.8. Ooh, too much, right? So let's try 6.7, too much. 6.6, it's still too much, okay? So we know it's somewhere between 6.5 and 6.6. Let's just try to the power of 6.55. All right, getting closer, right? 2 times 5 to the power of 6.555. Right? So again, notice that the more numbers that we add, the closer we're getting to 78,000. Not that we have to actually figure that out, but notice that the numbers I'm plugging in, this is the key. I'm plugging in decimals. Okay, so I'm not getting an integer. I'm not plugging in an integer, which means that this is not going to be a sequence. Okay, because again, it all comes back to what are you plugging in, right? Sequences domains are positive integer values, 1, 2, 3, 4, while functions are purely just any number we can use, okay? So things to remember, things to kind of remember about sequences is, and functions is this, right? Kind of a closing statement. All sequences are functions, but all functions are not sequences. Okay, so so it's important to know that you can say that all sequences are functions, but we can't say that all functions are sequences. Okay, so some of them are, but some of them are not. And that's it. That's comparing our sequences and our functions together.